Hi my dear brilliant subscribers, welcome to my channel. This is continuation of Glasstone and Sesonske, second chapter. In this video, we will discuss interaction of alpha particles and beta particles with matter. Before that, I will discuss Bremsstrahlung. What is Bremsstrahlung? You know X-rays. X-rays, generally we go to hospital whenever you have fracture to see what is the nature of the fracture. This X-rays, how they produces? X-rays are producing when fast moving electron enter into a medium, it will produce X-rays. There are two types of X-rays. One is continuous X-ray, another one is characteristic X-rays. Characteristic X-rays means when electron entering into the medium with high energy means high kinetic energy. What happens? This electron dislocate the innermost electron in the atom. When it is removing one innermost electron in the atom, there will be a vacancy in the ground state of that particular atom. Then in the same atom, the electrons in the higher energy, they will undergo transition and release the energy. That energy is called, that electromagnetic radiation is called characteristic X-rays. Characteristic X-rays wavelengths are fixed. It is different for different atom. Okay. So characteristic X-rays intensity is highest, the maximum. Out of this continuous X-ray and characteristic X-rays, the intensity of characteristic X-rays are maximum. Okay. Like this, characteristic X-rays are produced. How this continuous X-rays producing? When this electron is entering into the medium, it will undergo deceleration. When it is undergoing deceleration, that time it will emit the radiation. That radiation is called continuous X-rays. Okay? This continuous X-rays energy, the maximum energy of continuous X-ray approximately equal to energy of the electron which is entering into the medium. Okay? The average energy of this X-rays is much below compared with the maximum energy of that continuous X-rays. Okay? Here what happens, this electron when it enters into the medium, it is interacting with the atoms of that medium, it will undergo deceleration, it is undergoing braking its speed. So that is why this also called braking radiation, because the electron speed is braking, means decreasing. So because of this, these X-rays are produced. They are continuous X-rays. So this is one of the example for Bremsstrahlung. Bremsstrahlung is a radiation produced by a charged particle when it enters into a medium. While undergoing deceleration, it emits the radiation. That is called Bremsstrahlung. Okay? Not only this X-ray as an example, any radiation which emits due to the deceleration of a charged particle while interacting with the medium, that radiation is called Bremsstrahlung. So this Bremsstrahlung, high energy electromagnetic waves are gamma rays. This X-rays and gamma rays both are almost indistinguishable. What we can say perfectly about to distinguish them, gamma rays are produced from the nucleus. Gamma rays are coming from the nucleus due to transition of nucleons. Whereas X-rays are produced from outside the nucleus due to the electron transition from high energy to low energy. So this is only way you can distinguish X-rays and gamma rays. By seeing their energies, it is more or less they are similar. But this X-rays energy slightly lower compared to gamma rays. Okay, so this is what I want to tell you about bremsstrahlung. In nuclear reactor also, when fission happens, fission products emits a beta particle which is fast moving electron, interacts with the material particles of the reactor or even water. It will emit the radiation as a bremsstrahlung. Okay, now it is clear what is bremsstrahlung, what is X-rays, what is gamma rays. Now we will go for interaction of charged particles like alpha particle and beta particle with matter. The alpha particle is nothing but helium nucleus. This is a charged particle. When this charged particle moving with high kinetic energy entering into a medium, it is interacting with the atoms or molecules of the medium. What happens when this alpha particle enters? It will interact with the molecules and it can remove the electrons from the atom or molecule. When it is removing the electron from an atom, atom becomes ion. It is nothing but it is making electron and ion pair formation. When this alpha particle is interacting with the medium, it is making electron ion pair formation. So how can you say what is the intensity of this ion pair formation? So we can say which ionizing radiation, means alpha particle is ionizing, that's why alpha particle I can call as ionizing radiation. Similarly, beta particle also cause the ionization, that is also ionizing radiation. Out of this, which will produce high intense electron ion pair formation? For that we have one term, that is specific ionization. Specific ionization means number of electron ion pair formation per meter path length of this charged particle moved. It means the alpha particle traveled inside the medium 1 meter length. How many ion pairs, like electron ion pairs formation happen? So that says the intensity of electron ion pair formation. For example, if alpha particle traveling in air in 1 meter length, it will create ion pair around, order I am telling approximately. When alpha particle travels 1 meter length in air, it produces around order of 10 to the power of 6 electron ion pair formation per meter. 10 to the power of 6, order of 10 power 6. It may be 5 into 10 to the power of 6 or 6 into 10 to the power of 6 ion pair per meter. If it is a beta particle, it is around order of 10 to the power of 4 electron ion pair formation. Okay. So what is the reason? I will explain. This alpha particle has higher mass compared to beta particle. So when it is higher mass, if I take alpha particle and beta particle together, the alpha particle mass is 4 units and beta particle is electron, 0.00055 units. U is atomic mass unit, that you know. So the alpha particle mass is much heavy compared to beta particle. If you take two particles, alpha particle and beta particle of same energy, then alpha particle moves with slow. The speed of the alpha particle is much less compared to speed of the beta particle. When the speed of the particle is small, it can interact with the atoms or molecules of the medium for a long time. When interaction time is more and more, the probability of electron ion pair formation is more. That is the reason, even though alpha particle and beta particle have the same energy, alpha particle produces more electron ion pair formation. So specific ionization for alpha particle is much higher compared to beta particle. Simple example, for alpha particle, if it is traveling in air, it produces around 5 into 10 to the power of 6 electron ion pair formation per meter length. If beta particle is traveling same in the air, it produces around order of 10 to the power of 4 electron ion pair formation. Okay, now you understood. This electron ion pair formation depends on charge of the particle, mass of the particle, energy of the particle. Okay, so now you think fundamentally what is happening. When it is interacting with the medium, it has to remove electron from the material, from the atoms of a material or medium. So to remove the electron from the medium, if you take an example for air only, air, of course air contains most of the atoms or molecules of nitrogen. So to remove the one electron from the nitrogen or in the air, I will use a specific word in the air only. In the air means the molecule it contains. It will take around 34 eV, 34 electron volt energy spent. I am repeating, 34 electron volt energy spent to remove electron from the molecules of air. So 34 electron volt required for each ion pair formation. If you take example for a alpha particle of energy around 5 mega electron volt, it produces around 5 into 10 to the power of 6. 5 into 10 to the power of 6 ion pairs. Simply you can divide 5 mega electron volt divided by 34 you do. Like that you can calculate number of this electron ion pair formation. If you take the example of a beta, already I told you. Okay, now this is clear why alpha particle specific ionization is more compared to beta. Okay, now why we are not scared of this alpha particle and beta particle? You may get some doubt. Nuclear reactor you are operating, lot of alpha radiation comes, beta radiation comes. Why we are not scared of it? Why we are not fearing of it? The main thing is this alpha particle, when it is entering into a medium or even air, this alpha particle can be stopped. Alpha particle, the range of the alpha particle I will tell you. Range means what is the maximum distance it can travel in the particular medium. In the air, I will give the example. In the air, the alpha particle can travel up to 30 mm only, 30 millimeter. After 30 millimeter, that alpha particle velocity decreases to 0 and it will take electrons from the atoms of the medium and it will become helium atom. So alpha particle will die just by traveling 30 millimeter only in the air. If you take beta particle of same energy, the range will be 1000 times. 1000 times means it will be around 30 meter. Okay. So this alpha particle just 30 mm in the air, it can stop. So if you take a paper thickness of around 5 micrometer, this alpha particle can be stopped just by 5 micrometer thickness of a paper. So you can stop alpha particle even with a paper in your notebook. The paper thickness is around 10 micrometer. Within the paper, half of the thickness of the paper also can stop the alpha particle. Absorption of alpha particles. What we are going to do now, suppose alpha particle is coming from a particular source. I am doing this experiment in the air. I kept the source here. Alpha particle is coming, how much distance it can travel. How much distance I can detect this particle. That is the maximum distance traveled by the alpha particle before it died. That is the range. Okay. At the same time, we want to know what is the specific ionization of this particular alpha particle in particular medium. So if you plot the graph, specific ionization on the y-axis and distance from the source, how it looks, you see here. This is x-axis, this is y-axis, this is x-axis. This is I am taking distance from source, distance from source, or thickness of air, thickness of air, because I am doing this experiment in the air. So this is specific ionization, specific ionization. That you know, number of ion pairs per meter length of the path of the charged particle traveled. Okay. What you guess first thing? The particle coming from the source, the alpha particle coming from the source, immediately the energy of that particle is maximum. After traveling some distance, means at the moment when it enters into the medium itself, it starts interacting with the medium. So the energy of that alpha particle keep on decreases. Okay. Now the question is, just it entered into the medium, what is the specific ionization? After some distance traveled, what is the specific ionization? After long distance at the range, what is the specific ionization? That we are going to write. So certainly when it comes out from the nucleus and interacting with the medium, it will do ion formation. Okay. So let it be very beginning, the specific ionization will be somewhere here. Okay. As distance increases from the source, the specific ionization keep on increases. keep on increases. Okay. Why it is increasing? As it is going inside the medium, it is interacting with the medium. The velocity of the alpha particle is keep on decreasing. So it is getting more time to interact with the medium. So it is making more number of ion pairs. That is the reason as distance is increasing, the number of ion pair formation is increasing. After reaching some particular distance, what happens here? The graph looks like this, forms and suddenly drops here like this. So this portion is called, this distance from here to here, this is a range of the alpha particle in the air, because I have taken the medium is air. Okay. So what information we can get from this graph is, initially the specific ionization is less, as it is passing through specific ionization increasing because velocity is decreasing. Finally, near to the range, the specific ionization is maximum. After that, when it reaches to a velocity of approximately 0, almost 0, then specific ionization drastically decreases to 0. From the source, not only single alpha particle is coming, there are many alpha particles are coming. So I am putting source here, I am putting detector here, means not only single alpha particle is coming, many are coming. My question is, from this graph, can you say all the alpha particles have same energy? If they have same energy, they should and must have same range. Here you see, it's supposed to be exactly straight like this. At this point, it should be exactly like this. If each and every alpha particle that is coming from the source have the same energy, it must be like this. But a slight slope is observed in the graph. It means there are certainly some difference in energy levels, or different energy of alpha particles, they are coming from the source. But the difference is very, very, very less. Not like a beta particle energy. Beta particle energy is big spectrum. But here, the alpha particles which are coming from the source, they have energy levels approximately equal. Okay. So this is the importance of this graph. I hope you understood very well. And some more information I want to tell you. If you are taking different types of radioactive nuclides like thorium, uranium and polonium, they are undergoing alpha decay. Half-life, each radioactive nuclide has its own half-life. What is the relation between half-life and the range? Observation, what we observed from the data is, the smaller the half-life, higher the range. It means what? Half-life is smaller means it is emitting alpha particle with higher energy. Higher the energy, higher the range. You understood, no? So, from the data, this is information, just you remember. Half-life is related to the range of the particles. So, half-life is lower means range is higher. Remember this. Now, we will find out what is the stopping power of a material, of an alpha particle or beta particle. The range of alpha particle in the air is maximum compared to range of alpha particle in any material. of same energy. Alpha particle should and must be same. Okay, means same energy alpha particle, the range in air is maximum compared to in any other material. So the density, it depends on density. The most important thing what you have to understand is the air density is almost very less compared to water density and lead, iron or any material you take. Once the density of material is increasing, the specific ionization also increases because it interacts with more number of atoms and molecules. Because of that reason, the particle will not travel more distance in that medium because it will stop early. So we need to have one term, that is relative power, relative stopping power, relative stopping power of the alpha particle. Now we are going to discuss. So relative stopping power relative stopping power, the definition is given like this. It is simple formula. Simply the ratio of range of alpha particle in the air divided by range of alpha particle in the medium. So this relative stopping power of that medium, we can write like this. Relative stopping power is equal to range of alpha particle in air divided by range of alpha particle in medium. Definitely it is greater than 1 because I am taking the lowest density is air. Okay, so why we need to understand this? Based on this, you can design a material which can stop the alpha particle very quickly. Ultimately, that radiation should not reach us even though we are operating a nuclear reactor. So that is the reason we should and must know this relative stopping power. Okay, for example, this relative stopping power I will give you for water. This relative stopping power is 1000, means the value of relative stopping power is 1000 for water. And for our human body, tissue or even paper also, even tissue also, around 1000 times. 1000 times means compared to alpha particle in air, the range decreases by 1000 times. It means suppose alpha particle has range in the air 5 millimeter. If we use water as a medium, it will travel only 5 millimeter divided by 1000, that is 5 micrometer. So water, a thickness of 5 micron can stop alpha particle. Similarly, paper also, take a paper, the paper thickness is around 10 micrometer. The paper, this relative stopping power also 1000, so it will stop just half of its thickness. You understood, no? So this is most important concept we should know to design a material which can very well stop the radioactive particles. Okay, next what we want to design is, I am putting one material here like this. Alpha particles are coming and it should absorb in the material. So what must be the thickness? This is the thickness, no? This thickness must be equal to the range of the alpha particle in this medium. So I can design a material, whatever the area, how many particles are coming, what is the source dimension, accordingly how many alpha particles are coming and falling on the medium, that you have to calculate. When they are falling on the medium, what must be the thickness? This thickness must be equal to the range of that alpha particle in this medium. With that we can design a material. Okay. Absorption of beta particles we will discuss now. Beta particle and alpha particle, the major difference is the mass is beta particle is very less compared to alpha, that you know. Charge is beta particle negative, alpha particle is positive, and 2 times electron magnitude wise. Okay. But this alpha particle also coming from the nucleus, beta particle also coming from the nucleus. Alpha particles have definite energy levels, but a beta particle, it has energy spectrum. The energy of beta particle is not unique. It may be coming from the same source, continuously same source. If you take an example for iodine 135, it is undergoing beta decay. There are a lot of iodines out there, crores of iodines. From each iodine 135, what beta particle is coming, they don't have same energy levels. They have different energy levels. That is why beta particle has energy spectrum. Why? What is the specialty of beta particle? Why it has spectrum of energy? How that spectrum looks, we will draw here. Spectrum of beta particle energy. Beta particle energy. Okay. So if you plot a graph, this is y-axis, this is x-axis, this is energy. I am taking energy on x-axis. This is number of beta particles. Number of beta particles. So they have some minimum energy will be there. It's the maximum energy, not minimum. Somewhere it will stop here, not infinite energy. So this is the maximum energy. Maximum energy. Okay. So the particle of beta particle which is coming from the source, it has the maximum energy and it has some average energy or most probable energy and average energy. So that is why the beta particle don't have a particular range. The main reason is each beta particle have their own energy level. Higher the energy, higher the range, if medium is same. Okay. Suppose beta particles are continuously coming. You have medium air. In the air, one beta particle is reached up to here, another one reached here only, another one reached here only, another one reached here only. Depends on energy of beta particle. So how you have to design a material? The maximum energy of beta particle you have to take into mind. So for experimentally, what we come to know that the maximum energy of the beta particle will rarely exceed the 3 mega electron volt. Rarely exceed 3 mega electron volt. So you have to design a material which can stop a beta particle of energy 3 mega electron volt. Certainly all other beta particle will be stopped. So that is the advantage. By knowing this information, you can very well design your material which can stop the beta particle so that it should not harm you. Okay. Then you were taught maybe why the beta particle is happening. The beta particle is nothing but electron. The mass is same which is outside in nucleus, the orbital electron mass, and this mass is more or less is same. The only one thing is it is originating from the nucleus. It is coming from the nucleus, beta particle. How it produces? I will write simple equations. One neutron convert into inside the nucleus. Proton plus electron. Neutron charge is 0, proton charge positive, electron charge negative. Charge wise it is balanced. Mass also balanced. But spin is there, one spin. This neutron undergoes spin, off. Proton undergoes spin, off. Electron undergoes spin, off. Off plus off is 1. This is off. This is not balancing. It is not balancing means something else is coming. Based on this condition, they predicted one more particle should and must come. Theoretically they predicted. After that they concluded and they have found it. Really some other particle is coming. That is neutrino. Here I am calling that is antineutrino. Antineutrino. Plus some energy, whatever you call. Energy that depends on mass difference. It may be moving with some high energy. I can call some energy also releases. Some energy releases. That energy is nothing but the neutron was suppose not it is you assume neutron was rest. Suddenly become proton and electron. Proton is inside only but electron is coming out. Why it is coming out with some energy? There must be something else should supply it for kinetic energy. Why that beta particle is coming with high energy? Because some mass difference is there. Mass of proton plus electron plus this antineutrino negligible mass. If you take difference with the neutron mass, some mass will be there. Mass loss is there. Mass of neutron minus sum of the mass of proton plus electron plus antineutrino. There is a mass difference. Mass lost is there. That is converted into energy. With that energy only, this beta particle is moving with high kinetic energy. Now what happened? Your doubt is why this beta particle have like this energy? The first doubt. The reason is this neutrino sharing the energy. That mass defect equivalent binding energy of a neutron. Mass defect equivalent binding energy that is shared by antineutrino. Sometimes this is taking more, sometimes this is taking more. Or something is continuously momentum conservation happening and energy sharing takes place. So total energy one third beta particle will take, mostly 2/3 this neutrino will take. So most of the energy due to mass defect that is converted into energy, 2/3 is taken by antineutrino, 1/3 is taken by beta. So this is continuously varies. So that is the reason the beta particle have spectrum of energy. I hope you understood. Okay. With this I will conclude this video. You watch this video and you write down some important graphs like this and repeat. Definitely you will remember forever. Till next video, bye bye.